All right, 8.1, we're going to construct confidence intervals for a population mean, standard deviation known. Okay, so we're going to build an interval around a population mean that we don't have using the population standard deviation that we do know. We're going to do this with a point estimate. An estimate for a population mean is going to be a sample mean. And then we're going to calculate a margin of error. So basically we are going to take a sample and get a sample mean. We're going to calculate the margin of error and add and subtract that to the sample mean to create this interval that we're pretty confident that the real population mean of the distribution is in that interval. So for example, really quick, we're going to take a sample of 100 fourth graders. We have the population standard deviation. This is our sample mean. We're going to add and subtract the margin of error to create an interval where we think the population mean truly is. Alright, so it's all about this margin of error that we're calculating. The margin of error is going to be the critical z-value times the standard error. The critical value depends on the level of confidence, which we'll talk about. The standard error, because we have a sample mean and our sample size is larger than 30, the central limit theorem tells us that our standard error is going to be the population standard deviation divided by the square root of the sample size. So let's talk about the confidence interval itself. If we want 95% confidence, this interval is centered around the mean, so it's centered in my normal distribution here. So 95% confidence, we're going to cover 95% area under the curve, leaving us 5% not covered. But this is between two tails. So I have to divide that 5% by 2 to get the area left in these two tails. I can get the critical value is the z-value that matches that area under the curve, 0.025, on the negative side, because that's how my table reads, and it'll be the both negative and positive of that value. So really quickly, 0.025 is exactly here, so it's negative 1.96. That's where this critical value comes from. So to get the margin of error, I'm taking this critical value based off of the 95% confidence, so that comes from my yellow table, 1.96, calculate the standard error, which was 1.5, and that's my margin of error. Then we add and subtract it to the sample mean to get our confidence interval, so that we can say we're 95% confident that the true population mean is somewhere in this interval between these two numbers. So the terminology is the point estimate is a single number used to estimate the value of an unknown parameter. So for 8.1, we don't know the population mean. So our point estimate for 8.1 is a sample mean. It's what we use to estimate the population mean. The confidence interval is what we're constructing so that we're confident the unknown parameter is within that interval. The confidence level is the percentage that we use to construct the interval that we're told. They're going to give us, hey, what percentage, what of confidence level are you going to be using? And the margin of error is is what we calculate and add and subtract that to our sample mean. Critical value times the standard error. That is a sigma, even though it does not look like it. So finding this critical value, this critical z value, there is a table that lists common levels of confidence with the given critical z value. 95% confidence, the critical z value is 1.960. Where is this table? In chapter 8, we're going to be using table A.3. This strip for confidence z values is listed down here at the bottom of A3. So if we're constructing a 95% confidence interval, the critical z value is 1.960. Critical z value notation. If you notice, the level of confidence goes with this alpha. So before, when we had 95% confidence, if we want a 95% confidence interval, one take away that is going to be 5%. Then I have to divide that between two equal tails. So the area under the curve is 0.025. Using the yellow table inside out, it was exactly here at negative 1.96. And it's symmetrical, so that's going to be the same but positive. And you notice the notation, it's the level of confidence divided by 2 between the two tails. I also can use the bottom of my pink table to get 95% level confidence is 1.96. My critical z value is 1.960. So how do I get a critical z value for a level of confidence that is not on my cheat strip on table A3? Oh no, 92% is not there. I have to use the yellow table to get the critical z value that goes with this level of confidence. One take away the 92% confidence, I'm going to have 8% left over. I need to divide that between the two tails. I'm going to use the negative side of my yellow table to get the area closest to 0.0400 inside. That goes with my z, and I have 0.0401, and it goes with a negative 1.75. So the critical z value between the two tails for 92% confidence is 1.75. So for 8.1, our assumptions are we have the population standard deviation. That's why we can use z values. Critical z value goes when I have the population standard deviation. Also, the standard error, the central limit theorem says I can use this if my sample size is larger than 30 or it's from a population that's approximately normal. And my sample is a simple random sample, which means, hey, this sample truly represents the true population.